students, welcoming Gokul Global University webcast lecture. Dear students, how are you? I hope you all are fine. In previous lecture, we discussed about a synchronized counter with T flip-flop, a synchronized counter with JK flip-flop. It's a time diagram, it's a logic circuits, a synchronized counter binary mode 16 counter, a synchronized down counter, synchronized mode 16 down counter. So in today lecture we discuss about synchronized counter. Synchronized counter, binary counter, synchronized decade counter. Let's start. Synchronized counter. In the foregoing section of this chapter, the synchronized or a ripple counter were discussed, in which the flip-flop were connected in series. This counter were simple to design but have delay, which is the sum of delays of individual states. The total accumulated delay in the counter cause a limitation on the speed of a synchronized or a ripple count. In order to overcome this advantage, synchronized counters are used. In these counters, all the flip-flops are triggered simultaneously by the same clock pulse. Transition of all the flip-flop from present state to the next state will therefore occur at the same time, which reduces the delay of the counter. Synchronized counter can be designed by using JK flip-flop, D flip-flop or a T-type flip-flops. Next, synchronized binary counter. The manner in which the counts progress in binary count is shown in table 1.1. Here you see the output of synchronous counter. 4 T flip-flop are needed to design this binary counter. It may be noted from the table 1.1 that the output Q0 change its state for every clock pulse. So to get the toggle output of Q0 for every pulse, the T input of first flip-flop should be connected to high, means logic 1. The output Q0 change its state whenever Q0 is 1 and stores when Q0 is equal to 0. So the T input of second flip-flop should therefore be connected to Q0 output of first flip-flop. Similarly, output Q2 toggles when Q0 and Q1 are both 1, means Q0 is equal to Q1 is equal to 1, means logic 1. The output Q3 toggle when Q1, Q2, Q3 are 1. Also, here Q1 is equal to Q2 is equal to Q3 is equal to logic 1. Next, from the above discussion, the Boolean expression for inputs of all the flip-flop are given by. For the design of this counter, it needs 4 flip-flops. A table is drawn in which input are outputs of the 4 flip-flop, says Q3, Q2, Q1, Q0 used as the input in the table. The outputs Q3 through Q0 should be in binary sequence and resets after Q3, Q2, Q1, Q0 is equal to 1, 0, 0 and 1. So the Q3 is equal to 1, Q2 is equal to 0, Q1 is equal to 0 and Q0 is equal to 1. So the T0 is equal to 1, T1 is equal to Q0, T2 is equal to Q0 dot Q1 and T3 is equal to Q0, Q1 and Q2. Next, the logic circuit diagram of synchronized binary counter is shown in figure 1.1. Here you synchronize counter with T flip-flop which clock and clear. Next, it is clear from this figure that the clock input of all the flip-flops are connected together. This counter can also be designed by using 4 JK flip-flop. J and K input tied together, shown in this figure. Here you see the JK flip-flop connected with each other. Next, figure 1.3 show the waveforms taken at Q's output of all the flip-flop of synchronized binary counter. Here the waveform, all the waveform you see, first of all clock Q0, Q1, Q2 and Q3 waveforms. Next, note from the waveform that output toggle at the trailing edge of the pulse and output Q1 toggle when Q0 is 1, Q2 toggle when both Q0 and Q1 are 1 and Q3 toggle when Q0, Q1, Q2 all are 1. Okay? Next, synchronized decade counter. A decade counter, also known as mode 10 or a divided by 10 counter, can count from 0 to 9 and then it reset and count again. Let the counter counts in the natural binary sequence and it is designed using GK flip-flops. For the design of this counter, it needs 4 flip-flops. Next, a table is drawn in which input or output of the 4 flip-flops, say Q3, Q2, Q1, Q0, used as the input in the table. The output Q3 through Q0 should be in binary sequence and reset after Q3 is equal to 1, Q2 is equal to 0, Q1 is equal to 0 and Q0 is equal to 1. The JK inputs for each flip-flop for the transition from present state to next state are obtained from the execution previous table of the corresponding flip-flops. Next, this is shown this table output counter JK3, JK2, JK1 and JK0. Next, the K-map. Some student tell me, sir, what is K-map? K-map full form is Carnot map method. The Carnot method is very commonly used for the simplification of binary expression since no algebraic rules are applied in this method. It is simply a graphic method for provides a systematic approach for getting this simplified Boolean expression. If this method is properly used, then the available Boolean expression will be minimal and will not further be simplified by any method. The Carnot map, also called K-map method, suitable for this simplification. So I hope you all are understand Karnaugh map method. So the K map for J3, K3, J2, K2, J1 and K1 are drawn as shown in figure 5.1 in next slide. So the F and the expression for this input variable of JK flip-flops are given as J3 is equal to Q2 dot Q1 dot Q0 and K3 is equal to Q0. So the J2 is equal to Q1 and Q1 dot Q0, K2 is equal to Q1 dot Q0 and J1 is equal to K3 bar dot Q0 and K1 is equal to Q0. The expression for K1 may be taken as K1 is equal to K3 bar dot Q0 since it become equal to J1. So the J1 is equal to K1 is equal to Q3 dash dot Q0. Next, the expression for J0 and K0 may directly be written from the table 1.4 as J1 is equal to K1 is equal to 1. So in this K-map figure 5.1a you all this see, and also in 1.5b. First figure 1.5a is J3 is equal to Q2 dot Q1 is dot Q0 equation, and this figure 1.5b is for K3 is equal to Q0, and all these came up available here. Next, here figure 1.5c is J2 is equal to Q1 dot Q0 Karnaugh map here, and figure 1.5d for the K2 is equal to Q1 dot Q0 Karnaugh map available here. Here the figure 1.5e for the J1 is equal to Q3 bar dot Q0, and the figure 1.5 F 0 K1 is equal to Q0. Next, the logic circuit diagram of synchronized decade counter whose output will be in the state binary number is given in figure 1.6. Here you see the JK flip-flop joined with each other and lock plus and clear, and output mode Q0, Q1, Q2 and Q3 are available. Figure 1.7 show the waveform at the output of all the flip-flop. Here in this figure use all these the three modes available. First of all, ST is equal to store mode, C is equal to complement mode, and R is equal to reset mode. So the sequence of the counter can be verified from the waveforms. Okay. In next lecture we discuss about other counters. Okay. Thank you.